Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. The Great Attractor, a massive gravity anomaly in the universe. In the vast expanse of the universe, filled with countless galaxies, stars, and cosmic structures, there lies an enigmatic region known as the Great Attractor. This mysterious area exerts a massive gravitational pull on everything in its vicinity, drawing galaxies, including our own Milky Way, towards it. Despite its significant influence, the Great Attractor remains shrouded in mystery, its true nature still elusive to astronomers and physicists. This narrative delves into the discovery, exploration, and implications of the Great Attractor, a massive gravity anomaly that continues to intrigue and baffle scientists. The story of the Great Attractor begins in the late 1970s and early 1980s when astronomers began to notice a peculiar motion in the local universe. Galaxies, including the Milky Way, were observed to be moving towards a particular region of space at a remarkable speed. This motion was first detected through the study of the cosmic microwave background, CMB, radiation, the afterglow of the Big Bang that permeates the universe. By analyzing the CMB, scientists discovered that the Milky Way was moving at a velocity of about 600 kilometers per second towards the constellation of Centaurus. This discovery was puzzling. The movement of galaxies is usually influenced by the gravitational pull of nearby structures, such as galaxy clusters. However, the observed motion suggested the presence of a much larger and more massive structure exerting a significant gravitational force. This unseen entity was eventually dubbed the Great Attractor, hinting at its immense gravitational influence. To understand the Great Attractor, it is essential to comprehend the concept of gravitational attraction. According to Newton's law of universal gravitation, every mass exerts a gravitational pull on every other mass. The strength of this pull is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. In the context of the universe, this means that massive structures, like galaxy clusters, can exert substantial gravitational forces, influencing the motion of nearby galaxies. However, the Great Attractor is not an ordinary galaxy cluster. Its gravitational pull is far more substantial, indicating that it contains a tremendous amount of mass. To locate and study this massive object, astronomers employed various observational techniques, including redshift surveys and X-ray observations. Redshift surveys involve measuring the redshift of galaxies, which provides information about their velocity and distance. When a galaxy moves away from us, its light is stretched to longer wavelengths, resulting in a redshift. By measuring the redshift of galaxies in the direction of the Great Attractor, astronomers can estimate their velocity and infer the presence of a massive gravitational source. X-ray observations, on the other hand, allow scientists to detect hot gas in galaxy clusters. These clusters emit X-rays as the gas is heated to millions of degrees by gravitational forces. By studying X-ray emissions, astronomers can identify galaxy clusters and estimate their mass. This technique has been particularly useful in the study of the Great Attractor, as it provides a direct way to observe the hot gas and galaxies in the region. Despite these efforts, the Great Attractor remains difficult to study due to its location. It lies in the so-called zone of avoidance, a region of the sky obscured by the dense disk of our own Milky Way galaxy. This dense region of stars, gas, and dust makes it challenging to observe objects beyond it. As a result, much of the Great Attractor's structure and composition remain hidden from direct observation. One of the most significant breakthroughs in the study of the Great Attractor came with the discovery of the Norma cluster, Abell 3627. This galaxy cluster, located in the direction of the Great Attractor, was found to be one of the most massive and luminous clusters known. Its discovery provided crucial evidence that the Great Attractor is indeed a region of immense mass, capable of influencing the motion of galaxies over vast distances. The Norma cluster is situated approximately 220 million light-years away from Earth, making it relatively close in cosmic terms. It contains thousands of galaxies bound together by gravity, forming a colossal structure. The mass of the Norma cluster is estimated to be around 10 to the power of 15 solar masses, making it one of the most massive known galaxy clusters. Its discovery was a significant step towards understanding the nature of the Great Attractor, suggesting that it may be part of a larger complex of galaxy clusters and superclusters. Further studies revealed that the Great Attractor is not a single, isolated structure but rather part of a vast network of galaxy clusters and superclusters. This network, known as the Laniakea supercluster, encompasses our Milky Way and extends over 500 million light-years. The Laniakea supercluster is a gravitationally bound system of galaxy clusters, all moving towards a common center of mass, which includes the Great Attractor. The concept of superclusters highlights the hierarchical structure of the universe. Galaxies are grouped into clusters, which in turn form superclusters. These superclusters are interconnected, forming a cosmic web of filaments and voids. The Great Attractor, as part of the Laniakea supercluster, plays a crucial role in shaping the large-scale structure of the universe, influencing the motion of galaxies across vast distances. One of the intriguing aspects of the Great Attractor is its role in the peculiar velocities of galaxies. Peculiar velocity refers to the motion of a galaxy relative to the general expansion of the universe. In an expanding universe, galaxies move apart from each other, following the Hubble flow. However, the gravitational pull of massive structures, like the Great Attractor, can cause deviations from this general expansion, leading to peculiar velocities. The study of peculiar velocities provides valuable insights into the distribution of mass in the universe. By mapping the peculiar velocities of galaxies, astronomers can trace the gravitational influence of large-scale structures, such as the Great Attractor. This technique has been used to create detailed maps of the local universe, revealing the intricate network of galaxy clusters and superclusters. One of the most comprehensive maps of the local universe was created by the 2-Mass Redshift Survey. This survey, based on data from the 2-Micron All-Sky Survey, 2-Mass, measured the redshifts of over 45,000 galaxies, providing a three-dimensional view of the distribution of galaxies in the nearby universe. The survey confirmed the presence of the Great Attractor and revealed its connection to the larger Laniakea supercluster. Despite these advances, many questions about the Great Attractor remain unanswered. One of the biggest mysteries is the nature of the mass that constitutes the Great Attractor. While galaxy clusters, such as the Norma cluster, account for some of the mass, they do not fully explain the observed gravitational pull. This discrepancy suggests that a significant portion of the mass may be in the form of dark matter. Dark matter is a hypothetical form of matter that does not emit or interact with electromagnetic radiation, making it invisible to telescopes. It is believed to constitute about 27% of the universe's mass-energy content, significantly influencing the formation and evolution of cosmic structures. The presence of dark matter in the Great Attractor would explain the immense gravitational pull observed, despite the lack of visible matter. To detect dark matter, scientists rely on indirect methods, such as gravitational lensing and the motion of galaxies. Gravitational lensing, as mentioned earlier, involves the bending of light by massive objects, providing clues about the distribution of mass. By studying the lensing effects in the region of the Great Attractor, astronomers can infer the presence and distribution of dark matter. The motion of galaxies also provides insights into the distribution of dark matter. Galaxies within the Great Attractor are influenced by its gravitational pull, and their peculiar velocities can reveal the presence of unseen mass. By mapping the motion of galaxies, scientists can create models of the dark matter distribution, shedding light on the true nature of the Great Attractor. Another mystery surrounding the Great Attractor is its connection to other large-scale structures in the universe. The discovery of the Laniakea supercluster highlighted the interconnected nature of galaxy clusters and superclusters. However, the full extent of these connections is still not fully understood. The study of cosmic flows, the motion of galaxies influenced by gravitational forces, provides a way to explore these connections. Cosmic flows are like rivers of galaxies, moving towards regions of high mass concentration. By mapping these flows, astronomers can trace the gravitational influence of large-scale structures and uncover their relationships. The study of cosmic flows has revealed that the Great Attractor is part of a larger network of mass concentrations, including the Shapley supercluster, another massive structure in the nearby universe. The Shapley supercluster, located about 650 million light-years away, is one of the most massive structures known, containing over 8,000 galaxies. Its gravitational influence extends over vast distances, affecting the motion of galaxies in the local universe. The connection between the Great Attractor and the Shapley supercluster suggests that these massive structures are part of an even larger network, shaping the dynamics of the universe on a grand scale. The study of the Great Attractor and its connections to other structures provides valuable insights into the evolution of the universe. The formation of large-scale structures, such as superclusters, is influenced by the interplay of gravity, dark matter, and the expansion of the universe. Understanding these processes helps scientists unravel the history of the universe, from its initial conditions to its present state. One of the key questions in cosmology is the role of dark energy in the expansion of the universe. Dark energy is a mysterious force that drives the accelerated expansion of the universe, a accounting for about 68% of its mass energy content. The interplay between dark energy and the gravitational pull of structures like the Great Attractor shapes the evolution of the cosmos. The study of the Great Attractor and its influence on the motion of galaxies provides a way to probe the effects of dark energy. By mapping the peculiar velocities of galaxies, astronomers can measure the effects of gravitational forces and the rate of cosmic expansion. This, in turn, helps to refine models of dark energy and its influence on the universe. As our observational techniques and theoretical models improve, the study of structures like the Great Attractor will continue to provide crucial insights into the fundamental forces shaping our cosmos. The Great Attractor remains one of the most intriguing mysteries in modern astronomy. Its immense gravitational pull and its role in the motion of galaxies highlight the complexity and interconnectedness of the universe. While much has been discovered about this massive anomaly, many questions remain unanswered, particularly regarding the nature of the unseen mass contributing to its gravitational force. Future research, aided by advanced telescopes and observational technologies, will undoubtedly shed more light on this enigmatic region. The quest to understand the Great Attractor is not just a journey into a specific part of the universe, but a broader quest to unravel the mysteries of cosmic evolution, dark matter, and dark energy. Each discovery brings us closer to comprehending the intricate dance of gravity and mass that governs the universe, offering a deeper understanding of the cosmos.